Right, welcome along. Little video on one little thing we didn't do about the diffraction grating. Kind of missed it out. It's just a slightly awkward thing, and I thought that it might just get in the way if we tackled it in the other video, so I thought we could separate it out. So I'm just going to imagine a simple scenario. We've got some light, pretty much red light, 560 nanometers, and we're going to put it through a diffraction grating of 250 lines per millimeter. And the first question we might ask ourselves is, let's kind of draw a picture what's going on. Here's our laser light coming along. It's going to hit the diffraction grating, and then over here on a screen we're going to have some red dots, aren't we? Like that. N equals 0, n equals 1, I guess. And the first question we might ask ourselves, which is kind of a recap, but I make no apologies for that. What angle would that first dot be at? So we go to our equation, n lambda equals d sine theta. And then we think, oh, right, well, we haven't really got a d, have we? So we need to deal with that first. So d is 10 to the minus 3 meters divided by 250. I think I know what that is, but I'm just going to check. So that's 4 times 10 to the minus 6. So sine theta is going to be equal to the wavelength, which is 560 times 10 to the minus 9, divided by the wave, divided by d, which is 4 times 10 to the minus 6, and we have to do inverse sine of that, aren't we? So theta equals, so if I quickly do shift sine open bracket 560 x minus 9 divided by 4x minus 6 equals, and we get, as I hoped, about 8 degrees. So we can ask ourselves two slightly different questions, and this does get asked quite a lot. How many spots in total will be in our pattern? And also, how many orders will be visible? So we'll take the how many orders will be visible first. So we go back to the equation, n lambda equals d sine theta, and we think to ourselves, well, how do we get theta to be bigger? Well, we're changing n effectively, aren't we? As we make n bigger, sine theta becomes bigger. But sine theta is a very special function, isn't it? Sine theta can only vary between -1 and +1. So that puts a limit, an upper limit on how big n can be. So you're going to find your maximum value of n. You use either your maximum angle of 90 degrees to give sine theta is 1, or you just remember the maximum value of sine theta is 1. So we can say that n is equal to d sine theta over lambda. But the maximum value, so that kind of n max, is simply going to be equal to d, which was 4 times 10 to the minus 6, divided by lambda, which was 560 times 10 to the minus 9. So let's quickly do that. I was trying to remember to use the fraction button, because I would like you to as well. Although if you're using the 10 to the minus 6 button at the bottom, it's not too bad. 560 x minus 9 equals, and we get 7.14. Now, can n be 7.14? Well, no, of course it can't, because n is an integer. So what we're saying is n is equal to 7. Every time this is ever cropped up in an exam question, you get like n is equal to 3.7. And then, of course, the normal rounding rules don't apply. You can't round that to 4. 4's not possible. So in that case, n would be equal to 3. So if we're asked how many orders will be visible, or sorry, what will be the highest order visible, the answer will be 7. If we're asked how many orders are visible, the answer is 8 because we've got 0 plus 1 to 7. So this is highest. This is how many orders. And then finally, how many spots, or how many bright fringes would we see on the screen? Well, we're going to see one in the center, n equals 0, so that's 1 spot. And then we get 2 spots for every order, don't we? So we got 2, n equals 1, 2, n equals 2. So it's plus 14. So there will be 15 bright spots on the screen. Okay, thank you. I think that's the end of waves.